Thanks for joining us for another episode of DPC Radio. This episode was recorded live in Amsterdam at the Dutch PHP Conference 2012. For more information about the Dutch PHP Conference, visit our website, phpconference.nl.
All right, well, thank you all very much for coming along. When I saw the other talks that were put alongside this one, I didn't think anybody was going to show up. So you've either all seen those talks before or they were full up. So thanks very much for coming along. I spent the past 12 months working on a very large-scale, data-intensive project. My focus was the development of a PHP web application that supported displaying all of this information, processing it, reporting against it, exporting it, and just dealing with a huge amount of data on a daily basis. And that's what I'm going to talk to you all about today. So my name's Michael Peacock. I'm currently the head developer for a company called Ground 6, leading the development team there and managing the software development processes that we have in place. I'm the author of a number of web-related books, a couple on Drupal for my sins, and a couple on general PHP-related technologies. And occasionally I get to speak at events and conferences such as this. So thanks very much for having me along to speak. Just a very quick slide about the company that I work for, since they've given me the time to come here. We're a tech company based in the northeast of England. We focus on developing a range of web and mobile-based applications, whether it's ideas that the team have had themselves, whether it's ideas that the management have had, or whether it's external parties that have come to us and said, we've got this killer idea, but we don't have the technical expertise and we don't have the finances to do it. Can you help? And we also provide investment as part of that. So if any of you have got the next big idea up your sleeve and you're looking for money or you're looking for tech investment, feel free to get in touch with me after this or look us up on our website, because there's funding and tech support available there. So what I'm going to talk through today, this is a large legacy project that was developed as a proof of concept by a number of different contractors, designed to capture a very small amount of data for a small amount of collection units. As you can imagine, as something like that grew from a proof of concept to dealing with 1 billion pieces of information on a daily basis, there were a lot of problems that we had to face. So I'm going to tell you about some of the challenges, the problems, solutions, and approaches that we muddled our way through to try and support this huge amount of data, ranging from how we actually pulled the data into our servers, how we queried it quickly so that the user wasn't waiting around for the information to come out, how we reported against the data because there was a lot of interesting information in there that we needed, how we kept the application running, how we kept the application responsive, and also the issues that we had to deal with it being a legacy code base. As you can imagine, there's a lot to deal with there as a project of this size grew. This project relates to vehicle telematics for a company called Smith Electric Vehicles. That's one of their vehicles there. They're the world's largest manufacturer of all-electric commercial vehicles. And as I'm sure you can imagine, with technology like this, it's new, it's emerging, there's a lot of things that need to be worked out. So the amount of data that we get from these vehicles is phenomenal. The battery alone, which you can see there, has hundreds of subcomponents, each of which give us the current, voltage, energy usage, the state of charge and temperature every second. So just looking at some of the smaller components on there, you get a phenomenal amount of data that we have to deal with. Because of the way the project was structured, we had some specific constraints that we had to work with. The first was that we had to receive all of the data that was transmitted to us. One problem that we had is that the data was sold to government agencies as part of a deal with customers. They would get a subsidy when they bought the vehicle, and the government in exchange would receive some of the data. The cost of that was they wanted all of it, not just most of it. Also, if there was a fault on the vehicle and we didn't log it, then that might mean we'd have to send an engineer over there. With it being a new company, a new technology, we don't just have a service station around the corner, so we had to send engineers there. So we needed to make sure we got all the data. We had to keep it all as well as receiving it all. So in 3 years, the government might come back to us and say, we need that data again because we've lost it, so we needed to have it. We also need to compare it against how it performed in a previous year and the year before that to see how the information changed. So we had to make sure that we could keep it as well. We need to be able to display it in real time because engineers want to look at this information and see what the vehicles are up to. So that was important as well. And because we have deals with the government departments, we need to be able to transfer it to them as well. And also we need to look at the information that we've received and calculate information from it. So we know thousands of bits of information, we need to get some actual meaning from that. So we had to do some report calculations from that as well. A few bit of stats on the system. We have approximately 500 vehicles at the moment that are running on this particular system, driving around, giving us information. There's 2,500 bits of information every second the vehicle is running that we receive. And it's around about 1.5 billion MySQL inserts per day. You might notice the figures probably don't add up there, and that's because we only store the information if it changes. So if it comes to us and it hasn't changed since the last second, we don't need to store that bit of information. And we're the world's largest vehicle telematics project outside of Formula One. One thing you might realize with this setup of 500 bits of technology out there giving us information is we've actually built our own distributed denial of service attack and then pointed it straight at our own hardware. And the caveat of that is we have to actually keep the data that they're attacking us with. So that was a bit of a problem for us. We ended up with a sort of a constant minimum of around 4,000 inserts per second into our solution. So at any one time, that's normally how much is going into the cluster, with a peak of around 3 million inserts a second on a particularly good day. So first thing we need to do is to be able to actually receive the information from all these collection units, pull it in, store it into our MySQL solution, which is quite a challenge. First issue is that it's a continuous data stream. So in order for us to actually get that information, we need to be online. We need to have the capacity to process the information, because if we're online but we don't have capacity, we're just losing information or building a backlog that we have to process. And we need to be able to scale. Just because there's 500 vehicles out there driving around, we don't know when they're going to be used, at which time of the day. We don't know if one of them is down for maintenance. So at any one time, we could have more data coming at us, and we need to make sure the system can scale to support that. The biggest problem with that being the pressure of that information. If it all gets too much, then the whole system will just overflow with information. We'll not be able to do anything with it. We'll lose that information, and then we'll be in a situation where it takes us longer and longer to get back up to speed. Most of you are probably thinking, well, that's fine. You could just use cloud hosting providers like Amazon EC2, which can scale to meet the demand. We couldn't. We had two particular problems that meant we couldn't. The first was the company had already invested in 2 racks of servers for this project and thought, right, here we go. Here's some existing infrastructure you can use. And also, because of the data, we couldn't actually store it externally. We had to store it in our own offices. So we had a few problems there, which meant we couldn't use scalable hardware where we could just buy the CPU or the resources that we needed. Solution to that was to introduce a queuing system so that all the information would come in order in a flexible queue. Although we couldn't use EC2 for our own information, there was no reason that we couldn't for our queuing infrastructure. The queuing infrastructure didn't need to store the information permanently. It just needed to act as the delivery agent between the vehicle and our servers. So we were able to use cloud-based services such as EC2 to build a message queue that would support the information that we need. This had the benefit of, if our systems went offline, we had a message queue there that was building up information that we could deal with. It was fast, secure, reliable, and scalable because it was built on cloud-based systems. It was a hosted service that we went with, so we didn't even have to worry about the infrastructure ourselves. We just wrote somebody a check every month, and they dealt with it, and that was their headache. And we only have to process what we can. So if we did get too much information coming in one day that we couldn't deal with, we could just wait until a bit of dead time overnight and process that backlog. Of course, that doesn't scale in itself, but those trends tell us that we need to add additional processing servers to our own internal infrastructure and help us spot trends and patterns with the information that we've got. We went with a protocol called AMQP, which is the Advanced Message Queuing Protocol. It's an open standard, and if any of you have used Rabbit before, that's the protocol that they use, and that's definitely what I'd recommend. For a lot of the work that I've done myself with the message queue, I used the PHP AMQP library. You can either get it from GitHub or install it with Composer. It's a pure PHP implementation, so you don't have to worry about it working on Windows or Linux. You don't have to worry about compiling things. You can just pull in the dependency and run with it. And one of the good things about it is it's not just about pulling information from a queue, it can also push information. So if you've got queuing infrastructure that you need to deal with and you want to test some information, you can write a PHP application that pushes to your message queue some test information. I'll quickly run through how we use that to pull out messages from a queue before I quickly move on. So the first stage is create a connection to your AMQP server, specifying the host, port, username and password. You then create a channel, which is a logical link between your connection and the actual connection in the queue. You then link that channel to the exchange in the message queue. That's where all of the messages get relayed through. So you would say, right, we want to connect to this particular exchange. You then bind to the exchange and then select which queue it is that you want to connect to. And then all you have to do is say, here's what I want to do with every message, consume those messages, and run that callback with every message. So within a few lines of code, you're able to pull out messages from a queue and send them straight to a callback function that you've written. And it's just a case of waiting for any more messages that come in from the queue. Real nice, simple bit of code that you can pull from online quite quickly and get running. Problem with any sort of system is that you're going to get downtime. We'd put investment into this external message queue that was cloud-based, that could give us a lot of resources that we needed, but it's possible that it could go down and we could lose information that way, which is something that wasn't acceptable to the management of the company. Solution there was we made sure we had buffers within the application, both at our end and at the vehicle end. So if for whatever reason a connection dropped, it saved some information in a buffer for a short period of time. So now we've got information from the vehicle into our application. We now need to get it into our MySQL instance. We had a dedicated application which was connecting to the queue continuously, pulling that information and turning them into MySQL inserts. One thing which might seem obvious, but it's quite easy to overlook, is the load data in file with MySQL. Really gives you a lot of performance boost when you're doing a huge number of writes in one go. So what we did was we had our application pull the information in big chunks and turn it into quite large but very quick load data in file inserts. So we'd sort of say, right, listen to the message queue for 5 seconds, pull all that information, turn it into a single file, and then do a batch insert to MySQL. So you could really push the right performance of your database. It was very fast, and because of the high volumes of data that we were getting, although it was a huge amount of inserts per batch file, we were doing them so quickly that it would only take 5 seconds from queue to MySQL instance. So it still appeared as if it was real-time information to users. It was just a 2 or 3 second lag while we actually built up enough to do the insert. So now we've got a MySQL solution that's pulling in that sort of information, but you're going to want to be able to fine-tune your MySQL instance as well. So we've got the flush method, which we set to ODirect. This set the buffer pool to bypass the operating system cache and just use the NODB cache. For our use, we found that it was much more efficient than using the operating system cache, although it can have some negative consequences depending on what it is that you're doing with this approach. But for us, we found that we got a significant performance boost. We're also able to improve write performance by changing our log flushing. Preventing pre-commit log flushing just meant we got even more performance out of what we were doing. And finally, another one to look at there is your query cache size. Because our data was changing so frequently and most of our queries were related to new information, we were never hitting our query cache, so we actually turned it off because we had no need for it. So it's worth looking at the information that you're querying, how often your data changes, investigating how big or small that cache should be. In our case, we had to actually turn it off. And all of these tips are sysadmin approved. I'm not an expert in MySQL myself, but my colleague spent a lot of time tinkering with these numbers to get exactly what we needed. So we've now got a huge amount of information coming in that we need to deal with. And we're able to put it into MySQL, and that's great, but we need to actually do something with it once it's there. The original team of contractors, as part of their proof of concept, decided to introduce a small element of sharding. They said, well, you've got these 500 vehicles with information. You're never really comparing one with another, so why don't you stick each vehicle in a separate table? And that's what we did. We had it so that every vehicle had its own database that could run on any of our machines in the cluster. So the key there is to evaluate the data that you're pulling in and look for any natural breakpoints where you think you can offload it to additional machinery or additional tables. That'll give you some support for horizontal scaling. For us, it means as our message queues start to build up, because we're not able to process things quickly, we know that we can just slot in another server. Because of that sharding approach, we can then have more capacity quite quickly. This then gave us an architecture that looked something like this. We'd have a vehicle driving around, communicating with GPS to get its location. We'd transmit its information over the mobile phone network into our hosted message queuing service. We then pull from that constantly, turn it into inserts, and put that into our MySQL cluster. That was backed by an enterprise-grade SAN storage system as well, which we had to do some performance tuning on as well. And then we had a dedicated web server that served that information. So a key thing that we did was made sure that all of the hardware concerns were as separate as they could be, so that the processing didn't have an impact on the actual database servers when we're running queries, and if we had too much traffic to the web server, it wasn't going to affect the databases. You might be thinking, well, if your message queue could store that information, pull it in quickly and keep it there, then why do you have a problem? If they can do it, so can you. There's no real issue there. Well, the problem there is the message queue wasn't designed for storage. It was just designed for transportation, with some fail-safes if you did need to store it for a small length of time. We also transferred the messages in a compressed form so that we could get as much as we can into that, so we had to decompress it at our end. And also, because of the nature of this project, one message that was 16 characters long could actually contain up to 64 pieces of information that we'd need to put into MySQL, which exponentially increased the data size that we had. One important thing for us as a team was we really needed to find where our limits were. As a developer, it's quite easy to sort of think, well, I can keep tinkering on with this, I can experiment with these new technologies and see exactly what it is that I need to do to get more performance. But at the end of the day, you need somebody that's right for that job. And for us, we found that with this guy. He's the sysadmin that provided the slides earlier for MySQL. We have somebody specializing purely in MySQL who can sit there and tinker with things. So if you've got a system that's doing a lot with data and you're finding that a lot of your time is spent on research and development or troubleshooting, find somebody that can sit and just tinker with these things all day and improve your performance. A few things which Sam's posted about on his blog is the SAN storage system that we used. We found that most people just plug in the default configuration file and run with it. We found that we didn't get good write performance with that, so we had to tinker with some configurations there. So some information there on his blog. If anybody does have any big data MySQL problems, he's always welcome to be hit up on Twitter to talk through some of the things that he did. So we've now got information in our database. We're pulling it in, we're storing it there, that's great. But it's only good if we can actually pull it out and do stuff with it. So we needed to query it quickly. We needed to plot a lot of graphs that would show how a vehicle performed over a day. So that's the state of charge, slowly going down as the vehicle's driving around. That's 1 point per second just for that bit of information for a vehicle. It would take a little while to run. In general, we found we had quite a lot of long-running queries. As more and more vehicles came into service, that was becoming more of a problem. You'd have more people using the application, trying to pull information from it. And what they were finding is that everybody was trying to query information. Indexes were filling up the memory of the servers, and things were grinding to a halt. We found it really affected page load. It also introduced session locking. So if a user found that a query was slow and thought, right, I'll go to another part of the application for 10 minutes, their session would be completely locked out and they couldn't do anything. Exports were slow, so when we're sending the information to government departments, it was taking too long to pull it out. And also backing up, that was taking too long, and we needed to make sure we had the data safe and secure. With the real-time information that we had, the original database schema dictated that every bit of information we wanted had to be a separate query or bit of a subquery, just because of how it was structured. It meant that we had to do a lot of queries to pull out live information. We're looking at about 30 pieces of information on that live screen. So somebody would look at that page, and all of a sudden you've got 30 slow-running queries running in the background. And they would also refresh. So every 5 to 30 seconds, the AJAX scripts behind them would pull that information in again, which means you could get stuck in a loop with really slow queries. So the first thing that we did there was we looked at the number of requests that we had. We looked at how many AJAX calls we had. Originally, we were using something called fusion charts, which graphed every single thing as a separate chart with a separate AJAX request, which wasn't really good enough for what we needed. So we looked at that, we optimized it into a small number of charts with a separate request that pulled everything in as text. And that gave us something that looked like this. Just a few charts, and then all the other information that we needed came in through a single request. So that sped things up in terms of, gave Apache a bit of breathing space. Didn't really do too much with our MySQL solution, unfortunately. We also found that by having multiple points of entry into the application, with it being some legacy code, it was really difficult for us to change what the execution time should be, because we didn't know if it had been set previously or if something else required a previously set value. So one thing that we did was we looked at introducing a single point of entry so that we could say, by default, every page will time out after 30 seconds, and then we could override it when we needed to clean things up much better. One thing I'd recommend for doing that is the Symfony routing component. Allows you to define a YAML file containing all of your routes. You can then point your router to that file, tell it where your entry point is, and then it will give you a route based on that, and then you can act on the request. So that's a really useful tool if you're finding that you've got an application that's got hundreds of entry points and you need to consolidate it. You can just quickly pull that component in and tie things together quite nicely. We're still finding, though, that even though we'd improved Apache's performance by making a smaller number of requests, the queries were still very slow. So we were forced to shard it again. Because we weren't using something like an NoSQL solution, we had to do something quite dirty and look at the database schema again and break it up. So we split it into even smaller buckets. The data that we deal with is very much time related, so we might look at the information now, we might look at this week's information, but we're rarely having to compare yesterday to today or vice versa. So what we thought was, let's split it up into weekly chunks. So instead of it just being one database per collection point, we had one database per week per collection point. And that gave us a great speed increase. It also meant that we had to alter our application and do some other things which led to additional performance increases, which I'll explain in a moment. So we made a really simple PHP application that would pull in all the queries that we were running, look to see if we're doing it on that particular table, and then it would inject the correct table name into it. That was the easiest way for us to support this additional kind of sharding with MySQL not having any built-in support. So we wrote a really quick and dirty function that literally you passed it a date and it gave you the correct table name, and a sprintf meant that that went straight into our queries. The main benefit from sharding, though, wasn't actually splitting the data up, it was the excuse that it gave us. It meant that we had to look at the database schema in detail, we had to put some code in there, and we had to touch all of the queries. Because we had to alter all of our queries to say, we're doing something different, we were able to review the indexes to make sure they were optimal, and we're able to review the queries to make sure they were hitting them. And that was a big problem that we actually found. The two projects of sharding the database left it in a bit of a Frankenstein. So we had bits from really legacy applications still in the database, we had some new stuff in there, and we had some not so old, not so new stuff in there, which wasn't very good. When we looked at the index, what we found was there was the primary key from when it was all in one single table was still there as part of our index, and that was, I think it was a big int, so it was using quite a lot of storage space, filling up RAM when we're trying to query for something that wasn't even needed. So that was something that we're able to look at. It's a waste of storage space, increases your index size, and it increases your query time. So one advantage of the sharding was we were able to clean that up. We're also able to optimize the schema as well, because we had the excuse of being able to make changes there. Obviously, MySQL provides you with a range of different data types, whether it's different types of integer, different types of character, different lengths of storage that you need. One thing that we found was that we're using double precision for some of our numeric values when a float would have been perfectly sufficient. Problem was that meant that we're using even more storage space, and we also weren't using the right bit of the CPU when we're querying and doing computations based off that. So we're able to change that to a float and get even more performance. So one thing to look at in your application is keep reviewing your tables, your fields, your queries. Do you really need all that information? Does it all need to be in the index? That comes to query optimization. Something that we then started to do much more regularly was run all of our queries through an explain extend just to check that they were hitting the indexes. And where they weren't, we were then sitting down, reviewing the query, what it did, why the schema was that way, and trying to improve it. For any big queries that you've got that are hitting all of the data that you've got in your system, try and avoid things such as the cur date function and things like that, because they will prevent it from hitting the query cache. So if you avoid things like that, then you're more likely to hit the cache. So we've now got information, it's in our solution, and we can query it quickly. And finally, users are quite happy because the information displays relatively quickly. The problem is when they actually want lots of information in one go. So with a project like this, they wanted to say, well, I've got all these data points, and that's really interesting, but I want to know what that equates to for this day. So how much battery did he use today? How much energy did he use? How fast did he go? They're metrics that we're collecting, but on a per-second basis, which is useless. Not useless from an information perspective, but useless to management who wanted to look at that information. So we needed to be able to actually report against that information. We wanted information such as this, a really small summary that displayed information. And as I explained, it was just they wanted to find things like how far the vehicle travelled and how much energy it used. The problem with that would be we have to look up all that information from our query, and then we've got to do some calculations. So that was a bit of an issue. The trick that we found there was we're able to save these reports as things that we ran overnight. So instead of the user clicking and waiting 10 minutes for something to run, we do it ourselves automatically overnight. So we'd look at all the data and we'd do these reports. By doing it ourselves, we're able to also make sure that we kept things in memory for the length of time that we wanted. So if we queried one particular day and we needed the next day, we do that straight after instead of moving on to a different shard. So we're making the most use of the RAM that we had in the server and the most use of the index that we've got. We then just saved that information that we calculated as a single row in a single table. So we've still got a huge amount of information for analytical purposes and for graphs and charts, but when you need management performance information, we look at a separate table that's just got a small summary that gives them exactly what they need. It means that users and management can also aggregate the information. They're not just having to look at one bit of information, one bit of data in isolation. They can say, tell me about a week, tell me about a year, tell me about all these vehicles for this one customer. So by taking snapshots of your information and calculating performance reports, you're able to do that. As I mentioned, one of the things that we did as part of that approach was to group the queries together. So if we're looking at one day, we try and make sure that we did something that would also utilize the same index and the same things that we had in memory. And then it meant we had our performance information, but we could have it for a range of dates. So you could say, for these 20 vehicles, tell me how they all performed over a week. And instead of having to look through millions of rows that we have, we just look up a few rows in a single table, and that gave us the information that we want. So the main thing from that is we really need to look for efficiency savings in how we actually generate those reports and how we calculate that information. The initial reports that we had maintained a single connection to every database that we had. So for 500 vehicles that we've got, 500 databases, that's one PHP script maintaining 500 database connections, which is insane. So we updated it to maintain just one connection for each server, and when it was finished with everything on that machine, it would remove it. When it was finished with one particular database, it would just simply switch to the next database or the next table, instead of using all that resources on the web server and the application server. Another thing to do if you're compiling reports and storing the information is to make sure you make good use of the RAM in the servers that's running those reports. We found that while the queries would use quite a bit of the database server's resources, they didn't use anywhere near the full capacity. We might find that it was maybe 20 or 30% during the course of it running. So what we did was we set it up to run multiples at the same time, just with a simple modulo in the script that would say, run all the odd ones now, and all the even ones concurrently. So it would do one even, one odd, and then move on to the next. We just had a really quick and simple script at the top of our code that would do that with a quick modulo, so you can immediately get parallel running scripts. We also decided to start making some assumptions about the data. We needed to keep it all, but as I mentioned earlier, we didn't need to keep it if the data hadn't changed. That wasn't useful to us. So if a battery was at 100% at 10 o'clock and it was still at 100% at 10:05, we didn't need to know for all those seconds it was still 100%. So we made some assumptions, and we made some scripts that would look through our data and extrapolate the information from the database, so we wouldn't need to store quite as much. With that came this interlation library that we put together, which allowed you to inject a number of arrays with a common key, such as a timestamp, and it would pull out a single array with that same common key, but it would pull all the information together, so you could quickly look through it and get the information you want. A bit of food for thought when it comes to performance scripts or aggregating information is to also look at tools like Gearman. It's something that we didn't look at for this project, but they're really useful for scheduling background jobs, so it's definitely worth having a look at. So most of our queries were a lot quicker, but we still found the application wasn't as responsive as we'd like. We're still having things hang when the user was trying to click things on the page, and it just wasn't the best experience that we could give to users, which would be customers, management in the company, and government departments. They expected more. The first big problem was session locking with the queries. This was eased by the fact that we implemented a second bit of sharding, but to make the presentation flow a bit better, I've moved this to near the end. So this was actually before we implemented the sharding. We'd find that the session would completely lock out. And the reason for that was queries that were slow, PHP would sit there waiting for that query to finish before it would close the session that it had open. So the user would navigate to another page, and PHP would say, well, I'm not doing anything because your session from what you were doing before still hasn't closed, so I can't open your session again. And it would just sit there waiting. 10 minutes later, that query would finish, and all of a sudden, their browser would jump to the page that they'd clicked on. The way that we got around that was to ensure that we closed the session when we were finished with it, and then let the queries run. So instead of just letting the session close at the end of execution, which it does, we actually manually said we want to close the session now, which is using this not very commonly used function that just effectively closed the PHP session. What we could have done there is we could have offloaded it to the database, but the problem was we were waiting on database actions, and we didn't really want to be then sending additional queries to our database server. On reflection, though, one thing that we probably should have done is just use Memcache. Caveat to that is if you then need to use your session again within the same execution, you've got to reopen it. So once that query is finished, you've then got to reopen your session and deal with it. It's something that you've got to then keep track of, which isn't very nice. And it was made a big problem because we didn't have any templating in the original code. So with the real-time information, we were able to speed up our queries. We consolidated the requests, which made things a lot better. But the original design constraint still meant we were doing up to 30 queries per page, and that was loading every 5 to 30 seconds, which wasn't ideal. And for some information, customers wanted to look at all of their vehicles in one go. They wanted to see a map of where they all were, and that was just painful. So the solution for us was to implement caching, which, as I said, I wish we'd also thought about for sessions, but in hindsight. And with Memcached, all we had to do was create a connection to the server and then pull the information from Memcache. Our processing script that pulled the information from our message queue, all it did before it compiled its MySQL inserts was say, is this the latest bit of information for this particular vehicle? Yes. Put it into Memcache. So where you can, try and use caching for any real-time information that you're just going to throw away right after. It's really fast in-memory key-value store, and if you need any redundancy, you can look at the Moxie Memcache proxy. It acts as a single Memcache server to your application, but there's actually a number behind the scenes, and it can deal with failover when you've got issues. And the benefit of using things like that is we were then able to generate maps that showed all of customer vehicles across the world without having to query the database once. So we've got all our information, we're pulling it out, we're doing things with it, it's great, but we still had some problems with the code itself, the application being something that went from a proof of concept all the way up to a huge 1.5 billion insert a day application meant there were a lot of things that were creaking at the seams. First one was source control. We found that the initial application was using SVN, so we just moved to Git and we implemented a branch per feature strategy so that we were able to keep track of exactly what was changing and make sure that when we were rolling things out, we didn't have any deployment anxiety because we were confident with what had changed and we knew it was an isolated feature. Whereas previously it was just a case of, right, take whatever's in Subversion and stick it through FTP. And we also put automated deployment and build in place so that we had fallbacks and we could roll back to a previous version if we did make a mess. One of the problems with dealing with that sort of data is you get a lot of deployment anxiety because if you have a fault in your reporting scripts, then you find that a week later when you spot there's a fault there, you've generated thousands of bits of information, you've done all sorts of processing, and you found it's all wrong, and you've got to then waste CPU cycles doing it all over again, creating a backlog, digging yourself deeper into a hole of data. We also found that the dependency management in the application was very difficult to control. Templating wasn't thought of. Database handling was very difficult when we're swapping from different shards or different servers. Memcache, something that we introduced, wasn't easy to pass around, so we introduced dependency injection framework into the application to get around it. We also found that the original developer didn't use any form of auto-loading. All he did was set include path, and because he developed exclusively on a Mac, it seemed to work absolutely fine for him. But when some of our developers used a Windows machine, we found that it would look in one folder, it would have a capital case letter at the front, so it would fall back to another folder and get the right file. But for Windows developers, it would find the one with the capital letter at the front and pull that one in. So we introduced the PSRO standard to make sure that the code was a lot cleaner, much more maintainable, and we didn't have to worry about where's that file, where's it stored, when did we require it, what if we move it. It got rid of all those problems for us. We also had to worry about templates and sessions a bit more in terms of closing and opening the sessions to stop it locking. So we needed to make sure we had a templating system in place. Also, with the data being processed, we had to define how that was processed with effectively a dictionary of information which was stored in the database. So we implemented a patching system that would track any changes, back up the previous version before it made any changes, applied the changes, and then gave us a notification through our build tool to say, this particular date, we've rolled out new changes to your database. So if things started to break, we knew exactly where it was, both in terms of code changes and database changes. And for that, we just had a really simple script that looked in a patches folder, incremented an ID, ran that file using the MySQL multi, and then at the end of it, saved which patch it was up to. So, project now up and running, fully functional, we've got all that information, we can deal with it quickly. What does the future hold for something like that? Well, there's tiered SAN hardware, so you don't just have to stick all your information into hard drives and your SAN. You can get tiered SANs, which might say, this is information you're using all the time, so we'll keep that in memory, or we'll keep it in a solid-state drive. This is information that you probably aren't going to use, so we'll put it on a relatively fast, but not as fast as your solid-state drive. We'll put it there. Here's information from last month that you're probably going to archive soon. We'll put that on your cheaper commodity disks. And here's information that you really don't care about. We'll offload that to a remote drive somewhere else. And when you ask for it, we'll then load it, and you'll wait 10 minutes. So there's now tiered SAN hardware available that we could make use of to improve it. We could also use NoSQL solutions. The reason that the project used MySQL was because it was a bit of a golden hammer. The original team, they knew it well, and they knew how they could bodge it to get it to do what they wanted. It was also easier to find people that could develop in it, so when they needed to recruit members of the team, it was easier to get MySQL developers. But it's not necessarily the best option, and we had to introduce a lot of hacks and sharding that would often come out of the box with the likes of MongoDB. It's also worth looking at the data that you're actually collecting. If you're dealing with a huge amount and you're finding that things are starting to struggle, do you really need to keep it all? We were keeping it all because there was a lot that we had to keep, and there was other bits of information that we thought that could be useful, but we don't really know what it is. need to look at that data in detail and try and rationalize it and decide if you can get rid of some of it. I mentioned as well that we used a message queue to deal with inserting the information. There's no reason that a web application can't pull directly from that and display it as your real-time information. So when we had a live screen showing what a vehicle was doing and what its metrics were, there's no reason we couldn't tap straight into a message queue and just continually pull the messages from there, avoiding any caching and avoiding MySQL, and potentially even sending the information to the cache as part of that process. Of course, it's developed so we can scale horizontally, so we can add more hardware when we need to. So, if you're in a situation where you've got a crap load of data, what is it that I recommend? The main thing is that PHP really needs a lot of friends in this sort of situation. It's really good for displaying the information, processing it, reporting and exporting. But what it's not really good at is queuing it, inserting it, and visualizing it. So you really need other tools in your toolbox to help you with that. Continually review your application. Look at your queries, look at your code, your indexes, your database schema. Continually review it. Even if you're not making major changes, it's worth putting something in the calendar, maybe once a month. Just have a quick look at it and maybe see if there's anything that jumps out at you. And then a less regular, in-depth review where you rerun every query through checks. And also look for efficiencies in your code that you can improve and the number of AJAX requests. If you can, try and make use of message queuing. I think they're a really good safety net when you've got information coming in that you need to deal with. Queue what you can in terms of the information that you get through. Means you can move the data around within your application, and it gives your hardware some breathing space. So if you find that you can't cope with it, let your queue build up while you then build a new infrastructure or add new hardware to your application. When it comes to your code, make sure you've got some sort of template engine in there, whether it's just something that allows you to separate templating but doesn't do any rendering itself, or whether it's a full-blown template engine. Put some dependency management in there so that you can control exactly what it is that you've got within the application. Another problem that we had was things weren't very abstract originally, so things and meanings were hard-coded into the application that as we changed and as the data evolved, the code became out of date and didn't reflect what it was actually doing. Make sure you've got auto-loading in place, or at least a logical structure for pulling in your files, and also manage your sessions and your requests so that if you need to consolidate them, you can. And if you can, keep your related data together so that you can do any compiling and aggregate information. One approach that a lot of the analytics companies do is they'll look at storing per second data for this week, and then for last week you might only get hourly summaries, and then the week before and the month before you might only get daily and then monthly summaries. So if you can, try and compile the information. And that's me. So thank you very much for listening, and if you've got any questions, I'll happily answer them now.
DPC Radio is a production of iBuildings. The materials presented are copyright of the speakers. This episode is released under a Creative Commons Attribution, Non-Commercial, No Derivatives 2.0 license. iBuildings is a full-service web development company specializing in PHP development. For more information on how we can help you with your next web project, visit our site at ibuildings.com. Thanks for listening, and we hope you'll join us again for DPC Radio.